fully exploit this opportunity, and we will hear now about the selective interlayers in OPVs. Erin?
Thank you. Alright, so I wanted to start off with just a clicker question, just to see where we're all at, what page we're on. So, what do you think defines the VOC in an organic solar cell? So if you guys will weigh in, please. You guys have listened to me enough, you probably know where I'm going with this, right? So maybe the way I would approach this is, what gives you the biggest control? Okay, we settled? No? Yes? No? Okay. Alright, so, probably unfair question. But, generally we said, energy level separation of the donor and acceptor, so this HOMO-LUMO offset, plus this fudge factor of approximately 0.3 electron volts. We also had some work function of the contacts. Nobody thinks it's the transport level of the organics, and nobody thinks it has anything to do with kinetics. Okay. Alright, I completely disagree. I say that the VOC is predominantly defined by the kinetics. Okay? And I hope that I can explain to you why. And I think a lot of this has to do with my background as chemist / electrochemist, not physicist. So in my talks with physicists, we have different ideas about what kinetics and thermodynamics explicitly mean. Alright, so when I talk about kinetic region of an OPV, I'm talking about near the VOC. So I think what's come out in the literature in the last year or two is this: what is going on in an S-shaped curve in an OPV? What are these kinks? Right? I think in general, since the majority of you told me you were physicists, I think this is well accepted, and if you want to disagree, please, happy to discuss. But that in high reverse bias, you predominantly have drift, meaning that you have electric field dependence of your extraction. So you've overcome your barriers, and now it's just a matter of the charges get there faster based on the implied electric field. Okay, so why? Why the kinetic region in OPV? Well, what's happening at an OPV at VOC? Alright, so in the simple drift diffusion models, so if we've got drift at high reverse bias, we've got diffusion near no applied bias under light conditions. Alright, so what we've got then is a general flux at the contact or a current density. So with my electrochemistry background, I hear current density. What I really hear is number of charges per unit time, which to me sounds a lot like kinetics. Alright? And then the other thing that we've got going on is we've got recombination competing against us. Alright, so we know that recombination has some rate associated with it. And so at VOC we say, well, the photocurrent is equal and opposite in magnitude to recombination current, so therefore the voltage that at voltage we have zero net current. Okay? I think it's pretty well accepted that recombination has a kinetic term to it. It's got a rate. You generate charges, you have a certain amount of time to get them out of there before they recombine. Alright, so, question for you then is, kinetics, VOC, is that starting to make a little bit maybe more sense? Okay. So let's talk about this role of interlayers and OPVs, and specifically let's talk about these selective interlayers. So the way I define selective interlayer is the preferential harvesting of one charge over the other in the bulk heterojunction. So bulk heterojunction, we've got the donor and acceptor mixed together. Have a possibility of that the donor and the acceptor phase are in contact with both of your contacts. You've got both systems. So you've got this mixed potential happening at the contacts. All right, so we want to preferentially extract a hole on one side and an electron on the other side. Okay, there's a whole host of different interlayers that we've talked about today and yesterday. We talked about these phosphonic acids, which just act as a simple dipole. May or may not be selective. We talked about these tethered redox probes and how we can change charge transfer rates based on their orientation. Okay, so if I can change my charge transfer rate of extraction, so if I can slow down electrons, maybe I can collect holes faster. So maybe that's selective. Talk about polymer films. I think the one that everybody is familiar with the most is this P.PSS, this universal solution to everything, which was actually invented for anti-static mats in semiconductor industry and not for you putting on your oxide to extract charges. But it works. Or does it? Alright, and then there are what's come out in the last few years, and we've borrowed again from the OLED literature, and so these large band gap metal oxides. And I think this is where most people think about selectivity. Is we've got this large band gap, so what I'm going to do is I'm going to put a big band gap. So if I want to collect holes, I want to make sure that conduction band is so far above the LUMO that I've got this huge barrier to electrons, and so I'm going to preferentially pull out the holes. Okay, so coming from a chemist, I'm going to back up and say I think there's two types of selectivity. I think there's a thermodynamic selectivity, and I think you can have a kinetic selectivity. So what do I mean between the two? Thermodynamically, I mean you're just going to block the pathway. So again, these metal oxides. So for example, if I've got a large band gap P-type oxide on this side, I've made the conduction band high enough that I'm blocking electrons coming in from the acceptor. Conversely, on the other side, I take a large band gap oxide, maybe zinc oxide or titanium oxide, and I have a valence band that's very, very deep, meaning it's very, very far away from the Fermi level, very, very far away from the vacuum level. I'm hopefully trying to block this pathway for holes getting in. Okay? Now what do I mean about kinetic selectivity? Well, this comes back to our history lesson from yesterday, this photogalvanic cell, right? We have a donor and acceptor in solution, and I harvest one charge because it just is collected faster at that electrode than the other charge. It's gone before the other charge even has a chance. Okay? So we can kind of start to play this game. We can say, well, I want to just block the pathway. I don't want the charge to even have the potential to be collected. Or what I've done is I've kind of tweaked something at the interface, and so I've slowed down the other charge. And so my holes are extracted before they can even recombine with the electron. Alright, so again, this comes back to what does a chemist think about thermodynamics and kinetics, different from possibly physicists. Alright, the big underlying thing in thermodynamics is if something can happen. Is this reaction spontaneous? Yes or no? Relative variations of yes or no, but the question is, can this happen? Yes or no? Big thing with thermodynamics, there's no time built in, unless you use Marcus theory, right? Which that was the whole big point of Marcus theory, is it made a connection between an energy barrier and a rate. Okay, so when I think about thermodynamics, I think about it as an energy level diagram. Or, let's think about it as an energy elevator. Okay? You're in the elevator. You want to go to the 5th floor. Well, you can't stop at the 5th floor. It's under construction. So how can you get to the 5th floor? You can take the elevator any higher, 6, 7, 8, 9, and walk down. That's fine. But you can't get to the 5th floor from the elevator with the 4th floor. Stairs only go down. Okay? Does that make sense? If. Alright, what about kinetics? Kinetics is how fast something goes. Okay, so this is the time component of your reaction. So, for example, you can go from point A to point B, but depending on what's in your way, that's going to change how fast you go. So, for example, we're sitting on a road, wide open space, we're in Montana, nobody's around, We can go 100 miles an hour, that's fine. We get from point A to point B very, very quickly. Okay, now we're in LA. You don't get to point A to point B quickly, right? There's traffic in the way unless you have a Batmobile, right? Unless you've changed something about the dynamics of the system. You've changed the intermediate, you've changed the pathway that you're taking. All right, so how you get there. All right, so again, let's put it all in this picture. Thermodynamics, in the simplest sense, tells you the delta G of the reaction. So again, let's think back to our photovoltaic cell or inerts potential. If I put two metals in solution, will charge transfer happen, yes or no? Based on the thermodynamics. Based on this delta G, based on your inerts potential. Versus kinetics. How hard or how difficult is it to go from point A to point B? What's your activation barrier? What is your intermediate? How hard is it to make it? How hard is it to go from one side to the other? How stable is your reactant? How stable is your product? Okay, so let's talk about selectivity. So again, thermodynamic sense, what I've said is I've eliminated the if. I've said charge, you cannot go there. All right, so how do we think about thermodynamic selectivity? And so what I want to do is, this is a little different from the energy band diagram. So these are different redox probes with different redox values, or E1/2. And so I've tried to convert this onto an energy band diagram. And so we have two interlayers. One of them has density of states that extends all the way across the range of different redox probes. Okay, so with that density of states, it doesn't matter where I'm at, I can have charge transfer back and forth reversible reaction. The other interlayer on the bottom, I've shut off the density of states up here. I've shut off the pathway. I don't have any charge transfer that actually happens. And then if you put a redox probe near where you start to have the onset of the density of states, you can actually see that you have a completely irreversible reaction. You can go one direction, but you can't go the other way. And then at some point you have enough density of states down here that the redox probe can go forward and back, happy as a clam, reversible either direction. Okay, so this is what I mean when I say thermodynamic selectivity. I've shut off the pathway here for this redox transfer. You see a little bit of current just through sheer leakage or the KT. Alright, so let's talk about a couple of different interlayers. Specifically, let's talk about these large band gap metal oxides. Alright, and I'm going to focus for today predominantly on whole collection side, but you can imagine the equal, similar type dynamics and thermodynamics on the other side. Alright, so we want to collect holes. Well, we can do a p-type oxide, or I think what's come out in the literature is this n-type oxide. So moly oxide, tungsten oxide, vanadium oxide. And then on the converse side, we have these n-type high band gap materials. So nickel oxide, we've got this high band gap, we've got a conduction band that's very, very high relative to the LUMO of these organics. Alright, so what we think we've done is turned off the pathway. So we think we've made thermodynamic selectivity. Excuse me. But what is the mechanism behind these n-type oxides? What's going on? Alright, so again, we're going to focus on this whole collecting interface. So how do we get charges up? Well, we've got our donor and acceptor, we associate our exciton, we've got the free charge carriers where holes are moving through our donor. How do we get the holes out of the donor? Well, we talked about this work function. Alright, so work function represents the Fermi level. So you want to try and get your Fermi level of your material near the Fermi level of your oxide. You don't want to have a barrier to injection to go in. So converse of an OLED. Alright, we also want chemical stability, so we don't want any of these unwanted reaction mechanisms, unwanted activation barriers happening. So we'd like our interlayer with our organics to be stable. And then we'd like this idea of, let's talk about thermodynamic selectivity. Alright, so we want this conduction band to be high enough that we don't have electron injection in from our acceptor. Alright, and then we talked about interface states. So what can happen in an oxide? You can form interface states. What do I mean by interface states? I mean mid-gap states. So you may have the highest, you might have a conduction band that's really, really high. But if there's little pathways in here, there's little interface states within our gap, you now have a region where those charges can link through. You can have recombination. Right, so it starts to undermine your selectivity. Alright, so we've got, again, at our interface, we've got our TCO, which we're just going to assume has infinite density of states, metallic-like, and then we've got our p-type oxide, and then we bring in our donor, which has its own, and we're going to try and align our work functions as much as possible. From an electrochemistry perspective, the way I think about two materials is if they have different if they have different Fermi levels, when you bring them together, you have to achieve equilibrium. Right, so you're going to have charge transfer that happens. This is going to happen to some extent. Depending on how big the offsets are, depends on how much charge transfer you have. Alright, so we're going to look at what happens with work function, interface states, and again, this concept in the back of our minds that things are going to change. Alright, so we consider two types of contacts. This p-type, we're going to use nickel oxide versus n-type moly oxide. So what's so great about nickel oxide? Well, it's one of the few conductive p-type oxides. So what makes it p-type? First is that you've got this enthalpy of formation of these donors or acceptors, and so p-type means that the enthalpy of formation of acceptors. Right, so acceptors meaning that your Fermi level is going to move closer to your valence band. The other thing that's really nice about nickel oxide is that while most oxides, their valence band maximum is defined by this oxygen 2p, nickel oxide has nickel 3d orbitals. And so these orbitals actually form hybrid orbitals with the oxygen 2p, and so that you actually get those conductive d states that help add to the conductive mechanism of nickel oxide. You can also fabricate it by a whole bunch of different methods, some of which I think Joe hopefully went through. So pulse laser deposition, sputtering, and solution processing. You can electrochemically deposit it. You can deposit nickel metal and oxidize it on your surface. Alright, so this is the idea of this molecular orbitals. Again, everything is contributing. And so what we get is that we have this high degeneracy of orbitals with conduction happening predominantly through the valence band. Alright, so let's focus on solution process nickel oxide, since solution processing is so economically viable. Well, what does that mean? Well, solution processing, you mix a bunch of stuff together, you spin it down, and you hope that it's nickel oxide. And so what you notice is, I don't call it nickel oxide as an NiO, I call it an NiOX. Hopefully by now, you know that that has to do something with the near surface composition, meaning it's probably not nickel oxygen in a 1-to-1 stoichiometric ratio. The fact that it conducts, I know that it's probably not nickel oxygen in a 1-to-1 ratio, which is intrinsically not very conductive at all. So this is your band diagram for vacuum deposited nickel oxide. So we have a Fermi level and a valence band. And conduction band. So you do see that it's a little bit p-type, but the solution process from a nickel nitride precursor, we actually see that it looks very much more p-type doped. Right? And this has to do with the reaction chemistry of the nickel underlying. Okay, so I've got this messy oxide, and I want it to be thermodynamically selective. I don't want those electrons leaking through. Okay, so again, broken record here. That has to do a lot with what the oxidation state of my nickel is and how that defines my energy band diagram. So, pretty obvious I don't want to start with just pure metallic nickel. I'm going to collect anything, hole or electron, that comes through there. Alright, if I use intrinsic nickel oxide, not very conductive, I'm going to have quite the resistance through that. End of the day, not going to get much current. Alright, now we're going to use the solution process nickel oxide. Alright, that might work. It's comprised of actually nickel oxide and nickel hydroxide, and what that comes from is the catalytic effect of nickel. So people with a battery background are pretty familiar with this, that nickel can actually, the formation of the hydroxide is the precursor to oxygen evolution. Alright. But what about higher oxidation states of nickel? So if nickel 2 isn't very conductive, let's make nickel 3, right? Let's just make it very, very p-type. So how can we make nickel 3? Well, we can do a nickel oxyhydroxide, where you usually have a further complexation with water, and so you can get oxidation states of nickel between 3.2 to 3.8, depending on what's the near surface is. Or we have this nickel-3 oxide, okay? Well, what's interesting about these is that if you go through the spectroscopy of the two, the oxyhydroxide gives you this p-type that you want, and then you actually get an increase in your optical band, or in your electric band gap. All right, and this has to do with the dipoles that are happening on the surface. Conversely, when we dope nickel-3 oxide extensively, all right, so when we dope nickel oxide extensively with nickel-3 oxide, what we actually get is these unwanted gap states. And look where they appear. They don't appear down here near the Fermi edge. They actually appear right in the middle. Right in the middle where you would put your LUMO of your acceptor. So what is this? These are recombination centers right at that interface. All right, so a little doping can be good. A lot of doping, not so good, right? I mean, this is the classic OPV issue, no free lunch. Okay, so what happens? Well, let's take our nickel oxide. We've got two different types of nickel oxide, and one of them so what I tried to do is make not a classic electron-only device, but maybe a different way to think about this is actually a hybrid planar heterojunction. Okay, so I've got a p-type oxide and an acceptor. All right, so perfect rectification, donor acceptor, I should see just like a diode, right? We're not going to get really any photocurrent from this. We're just going to run it in the dark. Talk about what does the rectification look like. All right, so in forward bias, of course, I'm going to have electrons injected in from the metal through the LUMO of the PCBM, holes injected from the ITO into the nickel oxide. We have a nice recombination current in the forward bias. All right, but what about in the reverse bias? Now we're looking at leakage, which in the simplest sense, I'm just going to say charges going the wrong way, charges that we don't want to go that direction. So as we change the gap of our nickel oxide, so as we play around with this LUMO level, we actually can change the leakage level. All right, so this is my attempt to say, look, we actually do have this idea of thermodynamic selectivity. I can actually, by tuning the surface chemistry of this nickel oxide, I can tune whether or not those charges can go through there. Okay, now let's switch and let's go to moly oxide. So we've got a N-type semiconductor, very, very high work function. So high work function, what does that mean? Well, to me, high work function mixed with a donor with a relatively low work function, I bring those two together, I'm going to have charge transfer. All right, so out here somewhere, we've got a flat band, this is my bulk, but then near the surface, we've got a Fermi level that's in between the Fermi levels of the two. In the oxide, we actually have this accumulation layer, so we have electrons building up in the moly oxide, and then we have a depletion layer building up in the organic side. Okay, so is moly oxide an electron blocker? Yes, no. Yes?
Yeah.
What?
Not because of the energetics, but because what it accepts the electrons from the semiconductor, that hole that leaves behind that space charge essentially serves to screen carriers from being extracted.
Okay.
So it doesn't physically, thermodynamically block the carriers, but rather because of the space charge it develops, it screens.
Okay, so you're saying that the space charge region about the organic HOMO and the conduction band of moly oxide screen. Okay, you're going to preferentially harvest holes.
Yes.
Okay. How is that thermodynamically blocked? In the way that I put it. Can you still, so maybe ask the question another way. I'm glad you answered this because this is exactly the thing that I've wrestled with too, is what does the selectivity mean? So we've got conduction band from our moly oxide, and we've got our HOMO LUMO. We'll let this be be the LUMO of our acceptor. Okay? If I'm an electron, can I go here? Into the conduction band?
If you just looked at the interface, you would say yes. But what happens at the interface is because molten oxide is so strongly electroreceptive, you have severe band bending at the interface. So you create something of a local electric field due to that accumulation of charge. So in a way, you end up having selectivity because the electron doesn't want to be extracted because of the effect of that charge happening at the interface. So it's not intuitive, it's not obvious. But if you look at the UPS, you'll see very strong band bending like this. So literally, the electron does not want to extract this way because of that, what's happening at the interface.
So what kind of selectivity do you think it is?
You see,
Do you want to
okay, no,
go ahead? You want to
somebody-
help them out?
I
You wanna argue?
think we should also consider density of states.
Uh-huh.
If we want to see, because thermodynamics says, yes, it's possible, but the kinetics is depend on the density of state above the conduction band. So this electron tunneling, as far as I know, goes exactly to the same energy level into the, for example, molten oxide or something like that, and after that there is a thermalization.
Mm-hmm.
So this tunneling relates to the density of the state, and that shows that dictates the selectivity.
In what sense? What kind of selectivity?
Kinetics.
Kinetics. Okay. Do you agree with that?
So basically, he's arguing that this is kinetic selectivity. For me, the definition of kinetic selectivity would mean that I had some way to measure both rates of hole extraction versus electron extraction. You'd be able to say, okay, there's both being extracted, but holes is a higher rate, so it must be. So for me, the idea of kinetic selectivity is a little bit ambiguous because how do you measure if there is both carriers coming out? How do you measure what rate is larger than the other? So to me, I'm not really a believer.
You're a physicist, aren't you?
Yeah, I tend to look at it in terms of what the UPS shows. In terms of, in my mind, it's sort of like a physics picture. Is if I have an accumulation of charge at the interface, and that accumulation is creating like an electric field that's pushing charges away, essentially what you have is kind of like a membrane, essentially, created by the field at the interface. That's the way I see it. So the idea of the whole rate thing is a little bit,
Foo-foo.
yeah, I'm not a believer.
That's fine. Yeah. Anybody else? Really? No? Nobody? We all agree? No comments? Okay. All right. So, is molten oxide an electron blocker? So the series of experiments, and thank you everybody for who weighed in, because I think this does go back to, depending on what school of thought you're from, you change how you think about it. So Joe Barry hates when I go through this thermodynamic kinetic selectivity argument. His physics approach is, well, if you tell me the exact energetic positions of all of the intermediates, I can calculate the rate. Okay? That's true. That's great. But I don't think that you can start from a problem, you can approach a problem and know what all of your intermediates are. Which is why I make the distinction between thermodynamic and kinetic. Alright, so is molten oxide an electron blocker? So the series of experiments was done by Jens Meyer, who was postdoc in Antoine Kahn's group, now works for Philips. Alright, and so this is about to come out in Advanced Materials. And so what it is it's a series of experiments changing various different interlayers and trying to figure out, is molten oxide electron blocking? So we've got ITL, we've got C60, and then we've got 40 nanometers of C60, we've got 10 nanometers of an interlayer. So in a control device, that's just 10 more nanometers of C60. Another control is 10 nanometers of B10, which is this very, very large optical gap, electronic gap, organic material with a LUMO such that you do not have direct pathways. And then we've got 10 nanometers of molly oxide. And then on top, C60, and then our top contact. Okay. And so what you actually see is that in the control device, yeah, you've got a nice electron-only device. You've got in the forward bias injection from both the silver and electron collection from the ITO running directly through the C60. When we put the molly oxide in, we see a significant shift in this relative turn-on voltage. All right, so what we see is we've got a barrier. We try and inject electrons in, we've got a barrier. At some point, some potential, we overcome the barrier, and then you start to see just the general ohmic-like contact. And then with this BFEN, we can further increase this barrier. Okay. So now what happens if we change where the molly oxide is located in the interface? All right, so again, we've got a control down here. We've got ITO P dot with molly oxide on top, our C60, and then our top contact. And it seems to be directly on the control with just plain C60 with no molly oxide. So what this suggests is that's not really influencing your injection dynamics. Whereas if you take something like BFEN, you actually start to change where that injection is. But again, we're back to this idea of, but if we put molly oxide in the middle, we seem to change what happens relative to how those electrons move. So the question that pops up is, well, maybe molly oxide isn't as good as an electron blocker as BFEN, but it seems to be doing something when you put it in the middle of the C60. It seems to be disrupting. So what's going on? So if you do the spectroscopy, let's start out, we see the ITO with the pure C60 and a top contact, and so you get just this general energy level alignment, and you can see that the electrons can just go right through that thing, right? Which is exactly what we saw in our devices, right? So we see really low turn-on voltages and we see high currents at the same voltage relative to these other contacts. Okay, well what happens with this BFEN? Well, when we put this BFEN in here, you actually perturb the molecular level alignment. And so that you see that you've got this 1 electron volt barrier to go from the silver contact through the BFEN into the C60, that's fine. But then when you go from the C60 into the second BFEN, you have this 1 electron volt that you have to overcome. Okay? And so that's what you see here is that you actually do truly have electron blocking from the BFEN. So energetically, what happens with your molly oxide? Don't actually have the electron blocking from the molly oxide. What you actually get is an electron trap that sits down here in the middle when you put it in between, but when you put it at the interface. Okay, so when you have molly oxide at the interface with your acceptor in your bulk heterojunction, you actually have a direct pathway for electron collection, which is why when we move this molly oxide from in between the 2 acceptor layers to down here at the interface as we would use it in our bulk heterojunction configuration, we're not actually blocking electrons at the contact. But what we're doing is that we seem to be changing how we are harvesting our holes. Okay, so this is why I use molly oxide. I think about it, well, we don't have exactly as pointed out, we haven't actually measured relative rates of charge extraction, which is the next step. What we do think we've got is we've got a system where we energetically don't see electron blocking capabilities, but we do see a significant enhancement in device performance when we use these molly oxide interlayers. And so the real question is molly oxide acting as a kinetic selectivity, or are we missing something? Are we missing a thermodynamic component that we haven't pulled out from our spectroscopy? So I know traditionally we like to, when we give scientific talks, we like to end with a nice cute conclusion, everything all wrapped up in a package. But I think it also is useful to leave you with something to chew on as well. All right, so I don't have the answer for you, and if you guys would like to discuss, it's great. If not, we can certainly move on to the next speaker or the coffee break or whatever.
Thank you. In the previous slide, the slope of IV curve has not changed. As I can see, it has only relocated. So it means that it's not, maybe the interface between moly oxide and C60 or something like that is the kind of Schottky barrier junction or something like that, and not a recombination layer. Because if it was a recombination layer, the slope of IV curve should have been changed.
It was a recombination layer. So in this configuration, right, you're injecting electrons and everything is near n-type, right?
Yes.
So what's recombining?
So you said it's a kind of trap.
Yep, yeah, this one is. So when you put the moly oxide in the middle between the C60, what you get is this trap. So you inject from the silver, it goes through the beef-in contact, but since you've got this really high work function, you know, exactly as we discussed, you have this pinning on either side of it, okay? And so what you actually get is the electron comes through the C60 and then it sits in that moly oxide. How do you get it back into the next side of the C60?
So how these energy levels cannot accommodate with moly oxide? Because there is a slope on these energy levels.
In the moly oxide as well?
But in the moly oxide there is no slope.
Mm-hmm.
Why?
I think the rationale behind that was that the carrier density of moly oxide is such that the majority of the band bending is going to occur in the C60. So if you do the spectroscopy, if you put C60 on moly oxide, you see band bending happening over 30-some nanometers. If you put moly oxide on C60 and look at inside the moly oxide, you don't see hardly any bending.
Because of the peak.
So within the first couple nanometers, you look like intrinsic vacuum deposited moly oxide. So what this is, it's just a simplified representation. But yeah, I agree, there should be a little bit of pushback into the oxide as well.
So if moly oxide is a trap site, by increasing the concentration of charge carriers, these trap sites are filled. So after that, we should not see the effect of moly oxide.
Right, which I think is what his point was as well. Yep.
I think there was a question.
Yes, just to clarify for me the difference between kinetic and thermodynamic. So it would be a kinetic trap, you're saying, if there were phonon modes and selection rules that were governing thermalization rate down to the moly oxide window, and if there was no thermalization, you could just go across, modulate that, and that would be a thermodynamic or a kinetic trap.
So a kinetic trap, in I guess my sense would be an intermediate, right? So when we talk about thermodynamics, all right, so we have some initial state, we have some final state, okay? The delta G of our reaction is here. The kinetic process is going over the activation barrier and coming back down. But the actual delta G, is the reaction favorable or not, is between here. So again, this goes back to the arguments that I have with Joe Barry. He says, well, if I can draw these two, then I know what the kinetic, I can tell you what the kinetics are, because I can calculate, the delta G of going from here to here, and the delta G of going from here to here, and from that I can pull out the kinetics.
I just had a quick question about the thickness of the moly oxide. Does that matter in this case?
It can matter. So typically moly oxide is in the order of about 7, 10, 15 nanometers, depending on who uses it. And it can be quite insulating. So 100 nanometers of moly oxide is probably, not going to work.
But I mean, if you make it so thin that the electrons get some sort of a...
Just a tunnel barrier through that?
you can do that.
Yeah.
Further questions for Erin? Otherwise we will have now a long coffee break and we convene at 10:30. Let's thank Erin one more.